Okay, one of the topics that we're very interested in statistics, especially and in applications, is in prediction. We want to, given the information we have, what is the best possible prediction that we can make? And it turns out that conditional expectation is very closely tied to this, the answer to this question. So let's recall. So all the way back when we defined the expectation and variance, we realized that the constant, so we asked the question that uniquely minimizes the mean squared error, or the squared error loss is the mean. So is the value that C equals is the mean, provided that the technical condition is met. So okay, that we have finite second moment. So in other words, if this is our criteria, is to minimize this expectation, then the best way to do it, we should guess the mean. Okay. So now what we want to say is, well, suppose now that we have X and Y that have a joint distribution, and in this case, we'll assume that they have a probability mass function, then what function of X, so what function G of X best predicts Y in terms of X? In other words, now we're not, so in the first question, we're saying, I'm not going to tell you anything about X, Y, or anything. What's your best guess at Y? And your best guess is the expectation. Well, now what I'm going to say is, well, suppose you knew some information about X, and you knew how X and Y differ together, then what would be your best way to minimize this value? Right? So now we don't have to give a constant. We can actually give a function, something that varies with X. Okay. So let's see how this works. So mean squared error, by definition, in this case, is we're allowing our prediction now to depend on some function of a random variable X. Okay, so that's the definition. Actually, I don't want to do this. Sorry. That's the definition. But how am I going to deal with this? Well, I can use the Tower property. So it's the expectation of the conditional expectation okay. Now, what is that? Well, this can be calculated in terms of the distribution of X as expectation of Y minus G little x squared, given X equals little x, weighted by the mass function of X. Okay. So now for each X, the nth summand, so this is minimized. So for each X, this value we know is minimized by g of x equal to conditional expectation that x is equal to x. Hence, the best predictor is the conditional expectation of y given x. And the mean squared error of that prediction is the expectation. Now we're applying the Tower property again. Of the conditional expectation of the deviation from the conditional mean square deviation. This is exactly equal to the expectation of the conditional variance, which by the ANOVA formula, we can flip things around in the ANOVA formula. This is actually the variance of y in the ANOVA formula, but when we don't include the variance of the conditional expectation. So the variance of the error that we have is the original error, but we get rid of the error associated with the conditional expectation because we know the conditional expectation once we observe x. So that's an interesting way of thinking about what is conditional expectation of y given x. It's our best guess in terms of minimizing mean squared error. It's our best guess when we have as a function of x, it's our best function of x for guessing what y is given what we know about x.